Combinatorics is when you try to count using math, multiplication, division, things like that, how many ways like certain things can happen. Like, I don't know, if I take the letters A, B, C, D, how many ways can I rearrange those four letters? So A, B, C, D is one of the ways, but A, B, D, C is another. And if I keep going, we end up with 24 different ways, which is a lot of ways. We could have predicted that, though. If we go like this, if I have the four letters A, B, C, D, there are four different things that can go in sort of the first position. But once one thing, whatever it is used, there's only three things to be put in the second position, and two things to be put in the third, and one thing to put in the fourth. Sometimes this is drawn with one of these like tree diagrams, like A, B, C, D can be the first letter. But from each of these sort of leaves, there's sort of three branching out, because there's only three letters remaining, and then two branching out, and then from each of those, one branching out. So you can kind of see sort of this sideways tree would have 24 leaves at the end, each one representing an arrangement of the letters A, B, C, D. A permutation is an arrangement of things that have a certain order to them. And I like to use, as an example, imagine an ice cream place has 5 ice cream flavors. I'll just call them 1, 2, 3, 4, 5 to keep it kind of boring. Now, if I want to make a cone, a 2-scoop cone, I could make it like that, or I could make it like that. And these two cones, at least for me, do not count as the same experience. Maybe I like a different flavor on the top of the cone. Well, the number of 2-scoop ice cream cones I can make would be 5 for the flavor on the bottom, and then 4 if I'm not allowed to repeat in this situation. So 5 times 4 is 20. In math, we write that 5p2 is equal to 20. That means there are 5 things. I'm picking 2 out of the 5, but the order does matter. If I switch to cups and large cups, where these two things for our purposes are equal to each other, then there's fewer, because those are the same, those count as the same thing, whereas it counted as 2 separate cones. So that one would be 5 times 4 would be, if these counted as different, but they're the same, and every pair has sort of a partner that's the same, so I divide by 2 and get 10. Mathematically speaking, we say 5c2 equals 10. That's combinations of 5 things where we choose 2 of them, and the order doesn't matter, meaning if I take the same things in another order, it doesn't count as a new thing for us. So that's the difference between combinations and permutations. Now, if I move up to still the 5 flavors, if I go up to a 3-scoop cone, there are 5 for the bottom, 4 for the second, 4 choices for the second flavor, and 3 choices left, which is 60. So we'd say that 5c3 is equal to 60. Sorry, 5p3 equals 60. 5c3 for cups would be 60 divided by, it's a little tricky, when it was 2-scoop cones, I divided by 2. 3-scoop cups. 2-scoop cups, I mean. But for 3-scoop cups, I don't divide by 3. Instead, I'm going to divide by 6. Why 6? 6 because if I take any 3 flavors, I could actually make 6 different cones that have those 3 flavors in them. Those are not the same cone, but they would be the same cup. flavors 1, 2, and 3. It's a big cup, so it doesn't matter what order they're in. They all fit nicely near around each other. So he's divided by 6. And in general, that 6 is actually written, that's 3 times 2 times 1, which is written in math as 3 with an exclamation point. 3 factorial. Baskin-Robbins has 31 flavors, so a 4-scoop cup would be 31 times, 4-scoop cone, 30 times 29 times 28, which would be a very large number. 31C4 would be cups, that would be much smaller, be 31 times 30 times 29 times 28 over, not 4, but 24, 4 factorial. Now we can get official formulas for these things. So if I say like 10p2, that's just 10 times 9, and you stop there. It's basically the first two numbers of 10 factorial. That could also be written as 10 factorial over 8 factorial. Because if you expand it out, 10 factorial is 10 times 9. Instead of writing 8, 7, 6, 5, 4, 3, 2, and I'll just leave it as 8 factorial, and it cancels, and it ends up with 10 times 9 again. So the official textbook formula for permutations is n factorial over n minus r factorial. But for our purposes, it's going to end up as the first r numbers of n factorial. So when I see 10c4, I don't really think of 10 factorial over 6 factorial. I just think 10, 9, 8, how many do I have? 3, one more, 7. That should be a p. Now combinations, like 10c2, it's 10p2, but it's divided by 2 factorial. That accounts for all the repeats, like for 2-scoop cups, every 2-flavor combination we can make 2 different cones about. Whereas 10c3 is 10p3 over 3 factorial, because each combination can make 6 different cones. And in general, ncr is npr divided by r factorial. But npr could be written as n factorial over n minus r factorial. That's all over r factorial, which turns into a pretty famous formula, which is this. This is sort of the textbook formula for combinations. It's a pretty useful formula. To use it, I could say like 20c4 is 20 factorial over 16 factorial 4 factorial. Expand 20, 19, 18, 17. Stop when you hit the bigger number on the bottom. The smaller number expand, 4, 3, 2, 1. Cancel the 16s. While you're at it, cancel the 4 with something, cancel the 3 with something, cancel the 2 with something, and multiply what's left. 5 times 19 times 3 times 17, whatever that is the answer to 20c4. The nice thing about this formula is that it works if the numbers are large also, like 20c18, 20 factorial over 2 factorial, 18 factorial. Expand 20, 19, 18 factorial. Leave the 18 factorial alone on the bottom, but the 2 turn to 2 times 1, cancel, cancel. The 2 cancels with the 20, and that one's so small we can calculate out to be 190. So that's the basics between of permutations versus combinations. In the next video, we'll see some of the properties of permutations and combinations.